Alright, let's go ahead and see if I can hear myself. And it looks like I can. Next up, check our camera and see if I can see my hand moving there. And that looks like a yes. Okay, then we are good to get started. For once, I'm early by like a minute and a half. Okie dokie. Let's see what we need to do for today. So, of course, it's just, like I said last time, it's going to be an assortment of problems. We're going to start doing lots and lots and lots of problems for the next couple weeks at least, or next couple streams, I should say. I might be streaming multiple times a week over the winter break. That's not a promise yet. I have other things that I want to do over winter break as well, so we will see how all of that works out. I have other stuff to get caught up on, but I am thinking about it is the most important thing to remember. So where do we want to go today? There's only one little topic that we need to discuss, and we're just going to discuss it through problems. I guess we can talk about it before we do any problems, and that would be the topic of equilibrium. But other than that, we're just going to keep doing problems for the next couple streams, just so we can learn through actually doing the physics, some of the little intricacies of force that haven't been covered or slipped through the cracks over previous episodes, or whatever you want to call each of these streams. I guess it would be fair to call them episodes. Lectures? Yeah, I think lectures is also fair. Anyway, where do we want to get started? Actually, there's this problem over here. So I realized last week that I forgot to clarify that this is on a frictionless inclined plane, although that shouldn't be too much of a problem because that actually just turns it into two questions. What happens when the incline is frictionless versus when there is a coefficient of friction? You could have just considered both possibilities. So if you ever see a situation like this where there's some sort of missing clarification, some sort of missing detail, where the problem can be solved in more than one way depending on conditions that the problem didn't even tell you about, my recommendation is to just do both. Both, assuming that there's only two possibilities. If there's like 10 possibilities, then obviously that's not practical. But if it's a very manageable number of possible assumptions you could make, just try doing it under each of those assumed conditions, and that way you're showing that you understand while also subtly suggesting to the person who wrote the problem that, hey, maybe you forgot this little detail, maybe you left something out. Because that can happen on rare occasion on the AP exam as well. I mean, they write the exam and then they have a bunch of people look over it, and sometimes in spite of that, a problem that they assumed was very clear turns out to have something wrong with it that they don't find out about until students get confused by it on the day of the exam, and then a few days or a few weeks later they revise it and they might just strike it completely out of the tally so that it doesn't count towards your score, or give bonus points to the people who did somehow manage to do something with it despite the bad wording and other issues that the problem has. So that's just some general AP advice. If there's something wrong with a question, don't panic. Just do what you can with what you know and trust the system. I mean, I know asking people to trust College Board is too tall of an order. I don't trust College Board all that much either. But I guess trust isn't the right word. More like, it's not about trust, it's about reliability. It's about, there is a system in place to deal with this. And that system, at least, is reliable, based on what I've seen anyway. Okay, so without further ado, let's go ahead and talk about, I'm going to talk about equilibrium first, and then we're going to go to this. So equilibrium, really quick. Whenever you hear the word equilibrium in general, whenever you hear the word equilibrium in general, it means that there are two opposing things that work against each other, and at some point they just even out. So you've probably heard the term equilibrium if you've taken an economics course. You've heard about the equilibrium point when you draw a supply curve and a demand curve on a graph, and the point where they intersect is called the equilibrium point. You may have taken chemistry, where you may have learned about dynamic equilibrium, when there are two reactions happening at the same time and both reactions are the opposite of each other, and one reaction called the forward reaction is maybe turning two things into one thing, and then the reverse reaction could be that one thing then just separating back into the two things. And what's happening there is both of those reactions are happening at the same time. Both the forward and reverse reaction are happening at the same time, but eventually they happen at equal rates, so that the total change in the amount of all of those substances in your beaker or whatever is essentially constant. For physics, we are going to be looking at static equilibrium. Static equilibrium. I don't know why I wrote that S so far away. Static equilibrium. And when an object is in static equilibrium, that just means that the net force on it is zero. An object in static equilibrium is subject to a total net force of zero, is subject to a net force, oh goodness, I wrote that wrong, too much spacing, net force of zero. Now, net force being zero doesn't mean that the object isn't moving at all. It means the acceleration is zero. So if the object is moving, its velocity is constant. Constant velocity, which in most of our examples is going to be a constant zero, but it doesn't have to be, is the point. Constant velocity, not zero velocity, at least not necessarily. Constant velocity, not necessarily zero velocity. It's important to remember this because you will be given problems where you're told about an object that's moving at constant velocity, or usually the problem will say constant speed, and then you would assume from the context of the problem that we're talking about an object that's just moving in a straight direction, therefore that constant speed implies a constant velocity. And then from there you go, oh, then this object is in equilibrium, the net force on it is 0. And you proceed to do the problem from there. So yeah, very important to remember that constant velocity aspect of static equilibrium. It doesn't matter what the velocity is as long as it's constant. Typically it'll be 0, but don't be surprised by scenarios where it's not. So yeah, that is static equilibrium. Usually we write it as having the following condition mathematically. Mathematically, static equilibrium has the following requirements. Usually we're going to do this in, well, not usually, always. We're never going to go to 3 dimensions in physics 1 or physics C mechanics. I mean, well, kind of, but we're not going to work with the z-axis per se. But we might have to visualize a few things in 3D in later chapters. Static equilibrium requirements with an S. Mathematically, we would say net force along the x direction has to be 0, and net force along the y direction has to be 0. Whoops. What did I even do there? What is that? My brain isn't functioning today. Maybe today was not a good day to stream. Net force in the y direction also has to be 0. Or if it's an inclined plane, we could say net force parallel and net force perpendicular have to be 0. Whatever coordinate system you use, as long as your axes are perpendicular to each other, the net force along each axis is going to have to be 0. There is a third mathematical condition for static equilibrium, but we're not going to discuss that until a later chapter. I'll give you a little preview of it for now. This we're going to take for granted, but net torque should also equal 0. Net torque on the object should also equal 0. We have not learned what torque is yet, so this is for a future chapter. We're just going to assume that it is 0 for the current chapter, and once we actually learn how to work with this concept, we will start bringing it into our equilibrium problems. But for now, this one we can ignore. We will be ignoring that for today and for the foreseeable future until we get to the rotational dynamics chapter. Okay, now we can look at that problem from last time. So I intended for you to do this under the assumption that the incline is frictionless. So we have 2 masses. Let's see, where do I want to draw this? I guess we'll draw it over here. We have 2 masses connected by a pulley. Here's M1, there's M2, and the assumption was if M1 is greater than M2, if M1 is greater than M2, if M1 is greater than M2, and of course that angle, let's call that theta. If M1 is greater than M2, then under what conditions does the system of objects move clockwise, and part B, under what conditions does it move counterclockwise? Under what conditions does the system move counterclockwise? Counterclockwise. Does counterclockwise have a hyphen in it? I think it does. Otherwise, it's all one word. I guess that should be a capital U. Aren't you glad I'm not teaching AP English? I know I am. I would hate to teach that. I mean, I do care about grammar and all that, but English was always kind of that. I wouldn't say it was my least favorite subject. It was just one of those dull subjects where I didn't see the point in it most of the time. Grammar was intuitive to me, and literature isn't the most important thing to me, so yeah. I do think language is important, but I just feel like the way English classes are done could be better. Could be better. Maybe I'll make a video one day talking about what kinds of improvements I would like to see. But that's not our topic for today. So, assuming that this thing is frictionless, and then we'll also assume, well, let me think here. So, first off, the point where we split between clockwise and counterclockwise motion, the point where that split happens, is going to be the point where there's no motion whatsoever, right? You've got motion to the right, or clockwise, as I should probably say. You've got clockwise motion, you've got counterclockwise motion, and then the boundary between those, the boundary that splits those two types of motion, is when there's no motion whatsoever. So let's figure out, when does no motion occur? So I'm going to draw force diagrams of each object. I'll draw it over here. So here's M1. What forces act on it? We've got force of tension. Assuming a light frictionless pulley, the tension force pulling up and to the right here should be equal to the force of tension pulling up here, approximately. The difference between the two is negligible, so we'll treat them as being the same, as I elaborated last time. Now we have normal force, of course. And we have the force of gravity straight down, which can be decomposed into force of gravity cosine theta and force of gravity sine theta. Again, reminder on the AP exam, if the problem asks you on the free response to draw a force diagram, do not do this. Draw just the force of gravity straight down. Do not break it into components on your submitted diagram. Draw a second diagram with the components if you must. But if they ask for a diagram, they want raw forces, not decomposed into components. Anyway, that's it for the diagram of M1. For the diagram of M2, it's rather simple. We only have two forces. We've got the force of gravity downward, and I guess I should call these force of gravity 1 and force of gravity 2, but I think we can manage without having to make that distinction. And then we've got force of tension like that. Okay, and there's our two objects and their two diagrams. Now we've got two sets of Newton's second law equations to write. So normal force and force of gravity cosine theta are going to cancel each other out. So I guess we'll say net force perpendicular on object 1 is going to be 0, is going to be, I'll say, normal force minus m1g cosine theta, whatever that is, we don't really need it. And then net force parallel for object 1 is going to be, let's go with clockwise being the positive direction here. Let's go with clockwise being the positive direction here. So I want to go ahead and solve for, I'm going to assume that, or not assume, we were looking for the point where the acceleration of the system is 0. So net force, we're going to set equal to 0, and I'm going to do force of tension up the incline minus m1g sine of theta down the incline. And then we've got for our second object net force y on, I guess I should have numbered these 1, 1, and 2 for object 2. Net force y on object 2, we're looking for when the acceleration is 0, and given that I called the clockwise direction positive, I'm going to say that the force of gravity is positive this time, so that's m2g minus upward, we've got the force of tension. All right, and this first equation just gives us the normal force being equal to m1g cosine theta, which we could use if we added friction to this problem. We'll do that later probably. And then that just leaves us with these two equations, which we can put together. If I add these two equations to each other, then I end up with force of tension and minus force of tension cancel out, and then I've got m2g minus m1g sine theta. So 0 plus 0 equals m2g minus m1g sine of theta. And if I add m1g sine theta to both sides, m1g sine theta equals m2g. The g cancels out, which means it doesn't even matter what planet this pulley system is on. All that matters is as long as m1 sine theta is equal to m2, the system will be at rest. So then, that leaves us with the question of, what if one is more than the other? What if one is more than the other? If m2 is greater than m1 sine theta, then motion is going to be in which direction? If I write this more generally, if I had written this as m1 times acceleration of system and this is m2 times acceleration of system, then what I would have gotten for this equation instead would have been m1 plus m2 times the acceleration of the system equals m2g minus m1g sine theta. So if m2 was greater than m1 sine theta, then m2g would have been greater than m1g sine theta, which would have implied that this difference would be positive, which would mean our acceleration would be in our positive direction or clockwise. So if m2 is greater than m1 sine theta, then motion is clockwise, and then by similar reasoning, By similar reasoning, we can also say if m2 is less than m1 sine theta, then motion is counterclockwise. And there you go. We have solved it for the frictionless case. What if we add friction to the mix? What if I now put friction here? And let's see, if we're looking for the point where motion just begins, then we are talking about static friction. This one is going to be a little bit tougher, but yeah, we'll say that we have a coefficient of static friction, us, and this is, of course, even though I'm not writing maximum here, it is our coefficient of maximum static friction, because if we're looking for the moment when the system is just on the verge of moving clockwise or counterclockwise, then we're looking at a situation where the friction is already maxed out and holding on for dear life. So let's see what happens under those conditions. How do our diagrams change? Well, with friction, the direction of the friction depends on whether we're moving clockwise or counterclockwise. So if the system is on the verge of moving clockwise, then that would mean that the static friction would be pointing down the incline against the clockwise direction. So I guess I'll call this force friction CW for clockwise, and then similarly it would be up the incline if the system is on the verge of moving counterclockwise. So force friction counterclockwise. What I really should be doing, and CCW, by the way, is my abbreviation for counterclockwise, but yeah, what I really should be doing is drawing two separate diagrams, one with the clockwise friction force and one with the counterclockwise, but in the interest of saving time and space, I'm just gonna leave it like this. This is by no means a correct diagram, so don't do what I did here on your test, but just for the sake of saving space and time, that's what I will do for now. So let's go ahead and talk about the clockwise condition. So, clockwise scenario. In the clockwise scenario, force of friction would be down the incline like that, and our net force parallel on object 1 is going to be equal to, of course we're setting it to 0, is going to equal force of tension minus force of gravity sine theta, so that's m1g sine theta, and then minus mu static times the normal force. The normal force hasn't changed here, it's still going to be m1g cosine theta. That's what we got earlier. m1g cosine theta. Okay, and then net force y for object 2 is going to be the same as it was before. Net force y on object 2 is going to be 0. I should actually call them 1 parallel and 2 y. I think that's the notation I usually use. I'm not very consistent with that. Sometimes I put the number first and then the direction. Sometimes I put the axis first and then the number. I'm not sure why I do that. Anyway, we had just copy that over M2G minus tension force. I'm still going to use clockwise as the positive direction even when I do the counterclockwise scenario. So just a heads up for that. Put the two equations together. Add them to each other. 0 plus 0 is 0, of course. Equals, the tension force cancels out. I'm left with M2G minus M1G sine theta minus mu static times M1G cosine theta. And it looks like I can factor out, or not even factor out, just divide the whole equation by g. And once again, does not matter what planet you're on. Okay, and I guess what I would want to do here is just take these two terms over to the left-hand side. And that leaves me with what? Factor out, and I can also factor out the M1. So M1 times, we've got sine, we've got sine theta and mu static cosine theta. So that's going to be sine theta plus mu static cosine theta. Has to equal M2. So in other words, the system is on the verge of moving clockwise when M2 is equal to this quantity. In other words, when M2 is greater than this quantity, the system would move clockwise. Right? If I had just set this instead of 0, if I had just written mass times acceleration of the system, which, come to think of it, I probably should have done from the beginning. If I had just written it kind of like what I did here, M1 plus M2 a system, then yeah, it would be positive if M2 was greater than all of this. So M2 greater than M1 sine theta plus mu cosine theta will result in clockwise motion. But this time, we can't just say the reverse. We can't say if M2 is less than this quantity, then counterclockwise motion will occur. That's not necessarily the case. That's not necessarily going to be the case. So let me go ahead and start a new page for this. And let's see what happens in the counterclockwise scenario. In the counterclockwise scenario, the equation changes. In the counterclockwise scenario, that's looking a bit tilted. Okay, that looks better. Counterclockwise scenario. All right. Essentially the same equations, but there's a change. Net force parallel on object 1 equals, this time I'll actually do it, equals M1 acceleration of the system, which we will set to 0 in a minute, equals force of tension pulling it up the incline minus m1g sine theta, pulling it down the incline, and instead of minus, this time it's going to be plus, because this time, in the counterclockwise scenario, the force of static friction is trying to keep m1 from sliding down. It's trying to prevent a downward slide against the ramp or incline. So this time it's going to be in our up the ramp direction, which we're still considering positive for this problem. So plus mu static force normal, which is still m2, or no, wait, m1 g cosine theta, right? Yeah, m1g cosine theta. Okay. Straighten that out. Net force in the y direction for object 2 has not changed. It's just going to be mass 2 times acceleration of the system equals m2g minus force of tension. Now, if you wanted to change it and make the counterclockwise direction the positive direction, all that would do is this would be negative, this would be positive, this would be negative, this would be negative, this would be positive. So literally you just change all the signs, and that's the only difference that it would make. So I felt like it wasn't really necessary to do that when we could just copy all of our equations. Of course, that means that my expected acceleration of the system, unless it's 0, I expect a system in this scenario to be negative, given the way I've defined my directions. If clockwise is still positive and I'm looking at an object that's on the verge of accelerating counterclockwise, then I expect a sys to be negative here. Okay, put these equations together, and what do we get? m1 plus m2 a sys What did I do? Hold on. Let me try that again. M1 plus M2 a system. There we go. Equals, the tension cancels out, and we're left with M2G minus M1G sine theta plus mu static M1G cosine theta. I guess if you don't assume the acceleration to be 0, then the g doesn't cancel out. I mean, that's okay. So the acceleration of the system, I guess this time we'll solve it as an inequality from the jump. So I would want this to be negative. I would want this to be less than 0. So M1 plus, hold on. Let me think about this for a second. I'm trying to picture in my head how this is going to play out before I write anything down, and something feels off, but maybe I'm just thinking about it wrong. So M1 plus M2 a system, whatever this is, we expect it to be less than or equal to 0. So M1 plus M2 times the acceleration of the system in order for the thing to move counterclockwise, this has to be less than 0. But since this quantity is equal to this quantity, that implies then that m2g minus m1g sine theta plus mu static m1g cosine theta has to be less than 0. I can move all this stuff over to the right-hand side, and dividing by g isn't going to do anything. Dividing by a positive is fine. Just remember with inequalities, if you divide by a negative, you have to flip the inequality symbol, but g is a positive 9.8, so we are good here. Dividing everything by g just cancels out the g, and yeah, move these two terms over to the right. So counterclockwise motion will occur whenever m2 is less than m1 sine theta plus mu static m1 cosine theta. Okay, let me check and make sure that I didn't... Oh, and yeah, I can factor out the m1 is the next thing. So m2 less than m1 sine theta plus mu cosine theta. Okay, there we go. And if I just asked in general, under what conditions will the system move at all when friction is involved, then I can combine, whoops, forgot to close that parenthesis. Okay, there we go. What was I saying? Right, so if the question was under what conditions does it move at all, I can just combine the conditions for clockwise and counterclockwise motion and figure out between what two values will the system not move at all. And that's going to be, let's see if I combine this. So m2 has to either be greater than this or less than this. So m2 has to be between those two quantities. So m2 has to be greater than one quantity but less than another. So less than this quantity, m1 sine plus mu cosine, or greater than sine, wait, I'm missing, oh, hold on. Yeah, it was positive before and I moved it to the right, so now it's a minus. Okay, there we go. And then that would make this into a minus. And then our other condition was m2 greater than m1 sine plus mu. So that's going to be m1 times sine theta plus mu cosine theta. Let's see, does this even make sense mathematically? I feel like, hold on. I feel like this quantity would actually be smaller than this one. Although I guess it depends on what the theta is. Wow, there might actually be more depth to this problem than I first realized. Sine theta minus mu cosine theta. I mean, because of that minus sign, I would assume it's actually less than sine theta plus mu cosine theta. Our thetas are between 0 and 90 degrees, so sine and cosine of theta are both positive values in every inclined plane scenario we could imagine. So yeah, actually this has to be... Yeah, this doesn't make sense. Okay, I'm gonna think about this some more and hopefully have an answer by next week if I don't just outright release an individual video dedicated to this problem. It'll probably make more sense once I actually assign some numbers to these masses and see what happens, and also assign a value to theta. But yeah, this we'll look into for later. We'll look into for later. So let's not take this statement to be completely mathematically accurate just yet, because something feels wrong about it. I'll have to think on it, and of course you guys are free to think on it yourselves. But yeah, that's where I'm gonna leave it for today. Let's go ahead and look at some of those equilibrium problems now. Let's go ahead and grab a problem. Okay, so first up, I alluded to this problem last time. It says a 150 Newton bird feeder is supported by 3 cables as shown in the figure, which I will draw for you. Find the tension in each cable. So the way it was drawn, we have something like this. There's like some sort of ceiling or wooden plank that these cables are tied to, and then there's a third cable over there. And this angle they highlighted as 60 degrees, and this one is 30. Yep, it's a right triangle, so maybe something interesting will happen here. And then attached to that third cable is the bird feeder, which they didn't give us its mass, but they told us it's 150 newtons. They gave us its weight. They gave us its weight as 150 newtons. Okay, so what some people like to do with a problem like this is they like to treat it as if the object itself is right here at the intersection point of the ropes, which mathematically will get you the correct result, but I think it's important to understand what's really going on. What we actually have is 2 quote-unquote objects. Our second so-called object is going to be just this intersection point, this knot, where the cables are tied to each other. So I'm going to do net force, so I'm going to draw a force diagram for the bird feeder itself. Force diagram for the bird feeder itself, and then I'm going to draw a force diagram for the knot. And here's what we have for the bird feeder. We've got force of gravity equals 150, as I just showed. And there's going to be some force of tension. I'm going to call this force of tension 3. We've got 3 cables. We've got cable 1 and cable 2 and cable 3. So that's going to be force of tension 3 pulling upwards on the bird feeder. force of tension 3 also pulls downward on the knot. So force of tension 3 acts this way. And then we've got force of tension 1 acting in that direction. And force of tension 2 acting in that direction. Actually, force of tension 2 is going to be smaller than force of tension 1, if my math is correct. So this angle over here is going to be, well, if that angle is 60 degrees, then that angle over there is also 60 degrees, right? You have that sort of Z shape. We did a problem last time where we had to use that rule of geometry. Where was it? Where was the problem where we had to do that? Oh, yeah, right here. This problem from last time. Right, we had to look at, what's the official term for them in geometry? I think it was alternate interior angles or opposite interior angles between parallel lines. Anyway, so that angle is going to be 60 degrees, and similarly over here, if I draw a horizontal line, that should be 30 degrees because that over there is 30 degrees. So that should be at a 30-degree angle. Clearly I didn't draw this to scale. Yeah, I think force of tension 2 is going to have to be smaller, and we'll see why in a minute. Oh goodness. Maybe I really do need to get a new chair. The chair agrees. Maybe it's just the way I'm sitting. Okay, that's a little bit better. Okay, so net force on the bird feeder is going to have to be 0. This is an object in equilibrium. The net force on it is 0. We've done a few problems like this already, so we haven't really learned anything new except for the name of this type of problem. But yeah, net force vertical on the bird feeder has to be 0. Do I even need to write it out? Net force feeder has to be 0. So force of tension 3 upward minus force of gravity of 150 newtons downward, or you could have done 150 minus force of tension 3. Either way, you add one of the terms over to the 0 or subtract as the case may be, and you discover either way that force of tension 3 is equal to 150 newtons, which tells us that essentially the weight of the bird feeder is transferred through the rope to the knot and pulls down on the knot. But very important, I think, to separate the bird feeder from the knot so that we fully understand what's actually going on. Because this idea of the bird feeder applying its weight downward on the knot, I mean, I can understand why it's tempting to students learning this for the first time. It simplifies things, but it also prevents you from learning the truth. Anyway, net forces on the knot. So I'm going to do it in the y direction and the x direction. Let's do the x direction first. Net force on the knot in the x direction is going to be force to the right minus force to the left. To the right, I see adjacent to the 30 degrees is cosine, so force tension 2 times cosine, force of tension 2 times cosine of 30 degrees to the right, minus to the left, I would have force of tension 1 times cosine of 60. Force of tension 1 times cosine of 60. Okay. And of course, we set that equal to 0 because I don't expect the knot to be accelerating to the right or to the left. Similarly, I don't expect it to accelerate up or down, so net force on the knot in the y direction is also 0. The other reason you want to set it to 0 is because you don't know the mass of the knot. So if you wrote mass times acceleration here, what mass would you even multiply by? Anyway, in the y direction, I would have 2 positive y components for the tension forces 1 and 2, and a negative 150 from tension 3. So that's going to be force tension 1 times sine of 60 plus force tension 2 sine of 30 and then minus 150. Okay, well, we've got 2 unknowns here, tension 1 and tension 2, but the good news is we also have 2 independent equations in those 2 unknowns, so we actually can solve. We're just going to have to resort to good old substitution. Yeah, we can't just add the equations to each other and have one of our unknowns get eliminated anymore. So sad. So I guess the easiest way would be to solve this first equation over here for one of the tensions. I'll add tension 1 cosine 60 to the left. So force tension 1 cosine 60 equals force tension 2 cosine 30. And then I guess we can divide. Which one do I want to substitute? It doesn't really matter, but yeah, let's solve for tension 1. So this gives us force tension 1 equals force tension 2 cosine 30 over cosine 60. Yes, I could plug these numbers in right now, but let's see if anything interesting happens first. So now I want to make this substitution for force of tension 1 in here. And let's see what that gives us. I guess I'll also add the 150 over to the left-hand side while we're at it. So we've got 150 equals, so added that over to the 0 side, and then force of tension 1 gets replaced with this. Force tension 2 cosine 30 over cosine 60. That replaces tension 1 and then sine 60. And then plus force of tension 2 sine 30. And the 150 we already took care of. Okay, I can factor out force of tension 2. And also, I can simplify sine 60 over cosine 60 is equal to tangent of 60. Just reduces the amount of buttons you have to press on your calculator, but otherwise not really the most profound discovery here. 150 equals, I'll factor out force of tension 2, and then we've got cosine 30 times Sine 60 over cosine 60 becomes tan of 60 plus sine of 30. And then divide all this over, and we have force of tension 2 equals 150 over cosine 30 tan 60 plus sine 30. Okay, and now we can plug all that into our calculator and solve for tension 2 and then get a number which we can then plug in to solve for tension 1. Or we can solve for tension 1 in a similar way that we just solved for tension 2, just over here, instead of dividing by cosine 60 on both sides, we could divide by cosine 30 on both sides and plug that into force of tension 2 into this second equation. But I think we've done enough work, more than enough work for this one, so yeah, let's just get to calculating. Okay, so 150, whoops. Let's see, 150 over cosine 30 tan 60, and am I in degree mode? Yeah, it says so right there. Cosine 30 tan 60 plus sine of 30 is exactly 75. How about that? How about that? I wonder if we would have gotten that if we had just plugged in our sines and cosines up front. Probably not, because we would have rounded things a lot and gotten some decimals, and you probably would have ended up with something like 74.98. But yeah, there you go. Force of tension 2 is exactly 75 newtons. And that leaves us with finding force of tension 1. Force of tension 1 is equal to this expression over here. So force of tension 1. Oh, come to think of it, actually, this might be easier. Just take the expression for tension 2 and multiply it by cosine 30 over cosine 60. What would that do? I guess, well, it would undo this. I guess essentially what it would do is it would make this into a, I guess it would make it into, this would become, I think this would become cosine 60 tan 30, while this would just become plain old cosine 30. At least that's what my immediate intuition is telling me, but without actually sitting down and doing the math, can't say for sure. I don't want to do it, so we'll just let it go. Force of tension 1 is equal to force of tension 2, which we now know is 75, times cosine 30 over cosine 60, times cosine 30 over cosine 60. And this is probably not going to be a nice looking number, but we'll try. So we'll take our 75 and multiply it by cosine 30 over cosine 60. Okay, 75 root 3. Or if I multiply it by 1.0 to make it a decimal, 129.90. 129.90 newtons. guess force of tension 3 being 150. That's what it was asking, right? Find the tensions in the... find the tension in each cable. Okay, there's that problem done. Pretty simple in terms of just setting it up. And the math, while I made it a bit elaborate, it's actually not too hard. Maybe when it's your first time seeing it, but once you've done these enough times, you might just end up skipping the whole draw the diagram phase and immediately start writing your equations while seeing the diagram in your head. You can definitely reach that level with enough practice, with enough deliberate practice, I should say. Okay, there's, well, that problem I did in a different video, so I'll leave it for those who watch that video. Oh, here's one. So it says, find the tension in each cable supporting the 600 Newton cat burglar shown in the figure, and I'll draw the figure, of course. Once again, it's going to be an equilibrium problem. What color have I not used in a while? I guess the burgundy, maroon, whatever you want to call it. Okay, so we have a cat burglar who weighs 600 newtons. This is basically the same as the bird feeder scenario, except with a slightly different setup. We still have 3 cables, but we have the cat burglar, which is a person. I'm just going to draw them as a block for simplicity's sake. And they weigh 600 newtons. Force of gravity on them is 600 newtons. They're hanging on to a rope which is connected to another rope horizontally. This horizontal rope is connected to a wall, and then it's connected at an angle to another rope that is connected to some sort of ceiling. And they gave us this angle as 37 degrees. Which then tells us, if I draw this horizontal dotted line, tells us that this angle must also be 37 degrees. Okay, so I'm gonna, once again, number these ropes as 1, 2, and 3. And let's see what we can do. So the beginning of this is very similar to the bird feeder problem. In fact, the only major change is that this tension over here is completely to the left. Oh, let me double check. Was my intuition correct that tension 2 is less than tension 1? Yeah. Tension 1 is 129 and tension 2 is 75. Okay. Glad to see that my brain is doing something right today. Anyway, back to this problem. So we had, first diagram is just going to be the cat burglar. They've got a force of gravity downward of 600 newtons. And force of tension 3 upward. And if they're going to be in equilibrium, then tension 3 upward must also be 600 newtons. We can write the equation, but really, at this point, we've seen it before. You could probably skip that phase entirely. But net force Y on the burglar would have to be 0. Equals tension 3 minus force of gravity 600, implying then that tension 3 is equal to 600 newtons. Okay, so there's that. Then we've got, for the knot, we've got force of tension 1, and we've got force of tension 2. And we've got force of tension 3, which we now know is just equal to 600 newtons. Okay, tension 1 and tension 2. Well, I know since the net force horizontal has to be 0, since there shouldn't be any acceleration to the left or to the right, I know that, let's see, that was 37 degrees. I know that force of tension 2 cosine of 37, the adjacent component is to the right. I know net force not in the x direction. Wow, I'm even being inconsistent within the same problem. Object coordinate, object coordinate. I need to try and remember that. Object axis, object axis. Anyway, net force on the knot in the x direction has to be 0, so that means force of tension 2 cosine 37, force of tension 2 cosine 37 minus force of tension 1. I'm using right as positive and left as negative. That gives us force of tension 1 equals force of tension 2 cosine 37. We can use that later. And then net force on the knot in the y direction has to be 0. And that's going to be, well, there's no upward component to tension 1. There is an upward component for tension 2. So that's going to be force of tension 2 times sine of 37. And then downward, we've got the 600 newtons from tension 3, so minus 600. Okay, actually, we can just go ahead and immediately solve this. Sine of 37 is approximately 0.6. You might remember that the 37, 53, 90 triangle is a rather special one. Well, to be more precise, it would be 36.9 and 53.1. But, okay, I just drew a 45, 45. Hold on. No, I can do better than that. Let's see, 3, 4. Yeah, something like this. This would be, hold on, was it 36 point, hold on. Sine of 36.9 versus sine of 37. Yeah. So 53, or to be more precise, 53.1 something, and then 37, or to be more precise, 36.9 something. If you have these as your angles in a right triangle, then you just have your classic 3, 4, 5 triangle, or 6, 8, 10, if you will. I think it's better to think of it as 6, 8, 10, so that you get sine of 37 is 6 over 10 is 0.6. But yeah, add 600 newtons to both sides of this equation, and we get 600. Well, not actually, there's 3 quote-unquote sides to this equation, but, you know, add to the 0, and you get 600 equals force of tension 2 times approximately, they probably intended for you to use 0.6 here for the value of sine of 37. Divide by 0.6. Dividing by 6 makes it 100, and then dividing by 0.1 makes it 1,000. So force of tension 2 is about 1,000 newtons. Okay, and now we can solve for force of tension 1. If we go back to this equation, add force of tension 1 over to the 0 side, and we have force of tension 1 equals force of tension 2, 1000, times cosine of 37. If sine of 37 is 0.6, then cosine of 37 is going to be 0.8. And that's going to be 800 newtons. Let's see, does that make sense? Tension 2 is 1000 newtons. Yes, tension 2 does have to be greater than tension 1 because it has to have a component that's equal to tension 1. And a component can never be, is typically less than the full magnitude of a vector. I probably could have worded that better, but this isn't something you really need to know, but something you might want to practice to sharpen your intuition is being able to look at a diagram like this and being able to predict which of these forces will be greater or less than each other. Even if you don't necessarily have to learn how to do it at a glance, trying to learn that might give you some sort of advantage. It might, at the very least, as I always say, help you catch errors. If you make predictions and then you do your calculations and your calculations are not consistent with your predictions, well then, that gives you reason to pause and double check your work and potentially catch a fatal mistake. So, not the top priority, but definitely once you've mastered some of the more basic skills, once you've cleared all the fundamentals and learned all the necessary stuff, going back and training yourself on this, not even going back, just sparing a couple extra minutes per problem, looking at this and making a guess, and who cares if it's wrong, just make a guess, and that way your brain is just kind of subconsciously starting to think about this and starting to pay attention to patterns. You're not going to notice a pattern that you're not looking for after all. So yeah, just give it a quick look and make a guess, and whether your guess is right or wrong, your brain will start just kind of subconsciously trying to figure out why, and eventually you'll take notice whether you realize it or not, and you'll develop a feel for these sorts of things. Intuition can go a long way in saving your physics career. Or really any science career. If you're doing science, intuition is quite important. Anyway, let's take a look at another problem. What else do I have here? I feel like we've done enough equilibrium. That's an experimental design question. I think I'm going to save that for later, like after finishing everything. That's for like review for the AP exam. I'll have to remember to go back to this. Watch me forget. That one is a bit too easy. We'll skip that. Yeah, that's an easy kinematics question, so we don't really need that. Well, okay, there's one thing in it there's one part of it that might be worthwhile. Up to this point, well, except for these last two problems. So these last two problems have done something different than what I've been doing. which is instead of giving you the mass of an object, it gave you the weight of an object. And so far, we haven't had to do anything with that, except for just go ahead and use it directly. It just served to save us time. But what if the opposite were true? What if we are given the weight of something when we actually need its mass? That's where this problem comes in. Not the toughest problem in town, but at least it'll expose you to this idea. Let's see. First, let me blow my nose. Oh, winter is here, all right. Okay, I think we're good now. So it says, a shopper in a supermarket pushes a loaded cart with a horizontal force of 10 newtons. At least the force is horizontal, so there's that. They push a loaded cart. Let's see how well I can draw this. Yeah, that's not too bad. And then we'll give it little wheels. I'm probably putting more effort than necessary into these drawings, but there you go. Shopper in a supermarket pushes a loaded cart with a horizontal force of 10 newtons. The cart has a mass of 30 kilograms, so M cart equals 30 kilograms. And force applied equals 10 newtons. How far will it move in 3 seconds, starting from rest? They didn't mention anything about the surface that it's moving on, so we will assume no friction, because otherwise we can't solve with the amount of information given. And also, we're skipping that part. It's just asking us how far it'll move starting from rest. And net force is just going to be force applied to the right minus nothing to the left. There's a normal force up, canceling the force of gravity down, and no friction. So net force is just in the x direction. 10 newtons equals the mass, 30 kilograms, times the acceleration. Divide, and you'll get the acceleration and then plug into your second kinematics equation with time being equal to 3 seconds to figure out what your distance is going to be, how far the cart will move in 3 seconds. Excuse me. And then part B says, how far will it move in 3 seconds? Again, but this time, if the shopper places his 30 Newton child in the cart before he begins to push it. So I'm not going to solve the whole problem, but if 30 Newton child over here, if we let Newton Jr. over here sit in the cart, and his weight is 30 newtons, then what is the new distance? I'm not too concerned about calculating the actual distance, but let's at least figure out how we would go about finding the new acceleration. All you would have to do is figure out the mass of the child. So we've got force of gravity of the child, or weight of the child if you prefer, is, what did they say again? 30 newtons. You would just say then m child times g is equal to 30, and the rest is history. Divide by g, you got the mass of the child, and then from there you would just use mass of the cart plus mass of the child, mass total, times the acceleration, is equal to your net force, which is still going to be your applied force. And calculate the new acceleration from there. So yeah, that's all there is to that problem. That's the one and only thing I wanted out of that. I know it's probably self-explanatory to some of you, but if you had never seen a problem like that before, then it could catch you off guard. You might mistake the 30 newtons for 30 kilograms. Let's see what else we have here. Oh, this one's not too bad. It's pretty quick and simple, but at least it's something we haven't done before. So it says we've got a 2,000 kilogram car. I'm just going to draw it as a block. 2,000 kilogram car is slowed down uniformly from 20 meters per second to 5 meters per second. V initial equals 20 meters per second. V final equals 5 meters per second in a time of 4 seconds. Aren't you glad you listened to me and reviewed your kinematics? You did review your kinematics, right? I did warn you that it was coming, right? Okay, I'll stop guilt tripping. Actually, according to some of the stuff that I've been seeing in my YouTube studio, some people have actually been going back and reviewing the kinematic stuff. So if that's you, good on you. Anyway, questions are, what average force acted on the car during that time and how far did the car travel? We do not currently know the acceleration or the displacement. I'm assuming this car just moves straight. Otherwise, the equations of kinematics aren't really going to help us. Okay. So to calculate the force, we just need to figure out the acceleration. So I can just use the first equation of kinematics, would be perfect because I know 3 of the 4 unknowns in that equation, and the 4th one happens to be what I want, acceleration. So V final equals V initial plus acceleration times time. Be honest, how many of you forgot that? I did say to memorize these. And now you know why. At least I would hope. 20 equals 5 plus acceleration times 4. Okay, subtract 5 on both sides. We get 15. Divide by 4. 15 over 4 equals the acceleration. The velocities were in meters per second and time is in seconds, so the acceleration will be in meters per second squared. 15 over 4, well 16 over 4 is 4, so we're missing a fourth from 4, so that's 3 3/4 or 3.75 meters per second squared equals the acceleration. No calculator needed. And then they say what average force acted on the car during that time. But they also said that the car slowed down uniformly, so I don't know why they would ask for an average force. An average force would imply an average acceleration, but if it's slowing down uniformly, then you actually have a constant acceleration. But anyway, it's not the most important detail to worry about. The point is, we now take this acceleration and net force on the car is mass times acceleration. Mass of the car times the acceleration of the car is equal to 2,000 kilograms times 3.75. 3 3/4. Well, let's see. 3 times 2,000 is 6,000, and then 3/4 of 2,000 is 1,500. So 6,000 and 1,500 is 7,500 newtons. They could have made this more elaborate by asking us, you know, like they could have given us like some sort of friction or air resistance force that we needed to work against and calculate how much thrust we need from the car's engines, but that'll have to do for now. And then part B, how far did the car travel during that time? That's a kinematics question. You can just use the second equation of kinematics. I'll write it, but we won't actually solve here because we've already done some of this before. We did some force problems where you had to calculate the displacement, or distance rather. Delta x equals v initial times t plus 1/2 at squared is what you would do there. And for those curious, you can plug in those numbers and find out. Let me figure out what our next problem is going to be. Oh goodness, what did I do to my hand? I think I poked myself with a pen. Huh, that's... Well, I see blood coming out, but it's still like under the skin. I think I'll leave it alone for now. Anyway, the hunt for more problems. I probably could have done more preparation and actually picked the problems out in advance, but I figured it would be enough to just look through my videos and make sure I wasn't redoing problems I had already done in the past. Okay, here's one that involves kinematics. It says an object of mass 2 kilograms starts from rest and slides down an inclined plane 80 centimeters long in 0.5 seconds. What net force is acting on the object along the incline? The fact that it mentions inclined planes, you might think, oh no, I have to draw a whole inclined plane diagram, but in this case, since they're only asking about the net force, it's going to turn out that we don't even need any of that. It could have been, the problem could have been on a flat surface, and we would still get the same result. The orientation of the surface is not going to matter for this problem. So, 2 kilogram object starts from rest. Two kilogram object starts from rest and slides down an inclined plane 80 centimeters long. I guess we'll call this delta S, since it's not necessarily in the X or Y direction. Gets a displacement of 80 centimeters, and I'll treat this as the positive direction, 80 centimeters, which I'm going to go ahead and convert to 0.8 in meters. And that's for a duration of 0.5 seconds. So we've got time equals 0.5 seconds, and delta S equals 0.8 meters, and they said it starts from rest, so V initial equals 0, and I guess we'll leave gaps for V final and the acceleration. And it said, what net force is acting on the object along the incline? Well, to get net force, we just do what we did earlier. Get the acceleration, multiply by the mass, and we're done. So I guess we would want to use our second kinematics equation here would be the best choice. Delta S equals V initial times T plus 1/2 A T squared. So V initial is 0, so that's gone. And we know delta S is equal to 0.8. And then 1/2 A times T squared, 0.5 squared. Okay, multiplying both sides by 2 would take care of the 1/2. Actually, 1/2 times 1/2 squared over here is going to be 1/4 times 1/2 is 1/8, and then multiply both sides by 8. 0.8 times 8 is 6.4 meters per second squared for the acceleration. Okay, so that's one step, and then to get the net force, we would just do, I guess I'll do it down here in this remaining little corner. Net force on, what was it? They didn't even say, it's just an object. Whatever that type of object might be. So it would just be the mass, 2 kilograms, times the acceleration, 6.4 meters per second squared, which is going to give us 12.8 newtons of net force. I could ask a bonus question here. If the surface is frictionless, what is the angle of the incline? If there is no friction, find theta, where theta is, of course, the angle at the bottom of the incline. This is very doable. And of course, we're assuming this is on Earth. That's also an important assumption to make. How would we go about doing this? Well, we can draw the force diagram, and we will have normal force. Let me switch colors here. Let's do orange so that it contrasts well. We would have normal force pointing this way. So that's normal force. And then we would have force of gravity straight down, which decomposes into a cosine component that way and a sine component that way. So that's going to be force of gravity cosine of theta. That's going to be force of gravity sine theta. And that's it. And then net force perpendicular to the incline is going to be 0, and nothing of interest is gained from writing the equation for that, at least for this problem. If we needed to calculate normal force, it would matter, but we don't have friction, so we don't need the normal force for anything, so we can skip that and just focus on net force parallel. Net force parallel has to be, well, the 12.8 we just calculated. So 12.8 has to equal the sum of our forces in the parallel direction, which is only force of gravity sine theta, so 2 times 9.8 times sine of theta, and there you go. We can solve for theta. Divide by 2, divide by 9.8, or I guess if you want to do it all in one step, divide by 19.6. So 12.8 divided by 19.6 gives us that number, and then if I take the inverse sine of that number, sine theta equals this decimal number, so inverse sine of the decimal number gives me I'll round it to 40.8 degrees. So I get 40.8 degrees equals theta. And there you go. So like I said, I think it was last time actually, see if there are opportunities for you to ask yourself bonus questions like this. Just because the question originally didn't ask for this doesn't mean you couldn't wonder about it. Also, here's a question for you. What is the highest acceleration that you can possibly get for an object on an inclined plane, assuming the incline is frictionless? What is the highest possible acceleration you could get? That's something for you to ponder, but I think you will learn something along the way if you think about this question. One recommendation, just try a bunch of different angles and see what accelerations you'll get, and tell me if you can find a pattern. Some of you are really quick and might already know where this is going. But if it takes you more time, that's okay. You're still learning after all, and the people who figured it out quickly probably spent a long time honing whatever skills helped them recognize it so quickly. So the worst thing you can do is not think about it at all. The worst thing you can do is not practice. Don't worry about how fast you're moving through the course compared to others. Just worry about, are you facing forward or backward? If you're facing backward, that's a problem. But if you're headed forward through the course, then regardless of how fast you're moving forward, you're doing better than the people who gave up and stopped halfway or even went back. Anyway, let's look for another problem. Well, this one asks for final velocity, so I guess we could do it, but nothing too fascinating about it otherwise. And I already did that one in a past video from a couple years ago. I guess we haven't done one of these. This one, again, is rather simple, but just because we haven't seen it before, it might be worth looking at. It's going to be really quick. So it says we've got two objects with masses 3 kilograms and 5 kilograms connected by a light string that passes over a frictionless pulley. And they have a figure which I will draw for you, and then it says determine the tension in the string, the acceleration of each object, and the distance each object will move in the first second of motion if both objects start from rest. We will skip that last part and just focus on getting the tension and acceleration. So the drawing is this: a 3 kilogram object connected by a rope that goes over a pulley. So there's your pulley, and then a 5 kilogram object. And that's it. They start from rest and you let it go. Actually much simpler than the pulley problems we've seen before. What color do I want to use here? Yeah, let's use red. Okay, so simple diagrams. We've got mg, so 5g here, and then some force of tension upward on the 5 kilogram object. We've got a nearly equal force of tension upward on the 3 kilogram object, and 3G downward. And now all we have to do is determine a positive direction. I'm going to say a positive direction is going to be clockwise. For obvious reasons, the heavier side is probably the side that's going to drag the whole system in its direction. And let's write some net force equations. So I guess I'll call this object 1 and this object 2. So net force on object 2 in the y direction is going to be, if clockwise is our positive direction for the pulley, then down is positive for this 5 kilogram object. So 5 times acceleration of the system equals 5G for our positive force and minus tension. Okay, and net force for object 1 in the y direction is equal to 3 times the acceleration of the system equals up minus down in this case, so force of tension minus 3G. Okay, add the two equations to each other, and we get 8 acceleration of the system equals 5G minus 3G is equal to 2G, and the tension forces are just gone. And divide by 8, and the acceleration of the system is 1/4 of G, or G over 4 meters per second squared. Well, I guess the meters per second squared is already contained within the G, so writing it like this would be writing 9.8 over 4 meters per second squared, meters per second squared. So I guess we don't actually need this until you plug in G, because plugging in G is both plugging in the number and the units. Anything else for this? Oh, right, finding the tension. So just plug in G over 4. Actually, yeah, let's keep it like this without plugging in numbers and see what happens. No, don't want to use orange. Let's use a darker color. Let's use this purple. So if I plug in G over 4 for the acceleration of the system, and I do it over here, then I'm going to get 3 times G over 4 equals the tension minus 3G, force of tension minus 3G. So that's 3/4 G equals tension minus 3G. So adding 3G to both sides, well, the 3G is 12 over 4G. So 12 over 4 added to 3 over 4 is 15 over 4 G is equal to the tension force. And of course, in the end, you would actually plug in G and give a number, but if you were given some sort of expression problem where you're not supposed to have a number in the end, this is probably what it would end up looking like. And I guess a bonus question that I can ask you to think about, kind of similar to what I asked over here, in fact. How high can the tension go? If you keep the same total mass, but you change the masses around, what if you change, instead of 3 and 5, what if you reduce this by 1 and increase this by 1? What if you make this 2 and this 6? What if you make this 1 and you make this 7? What if you make this 1/2 and you make this 7 1/2? What if you make this 1/4 and you make this 7 3/4? What happens eventually as more and more of the total mass ends up on one side of the system versus the other? What happens to the acceleration of the system, and what happens to the tension in the rope? How high or low can those two things go? Is there some sort of limit? Is there some sort of number that they seem to not go over or under? Is there some sort of minimum or maximum to take into consideration? Those are some things you can ask yourself. Just trying to show you how you can add more to a problem. Even something as simple as this, you can add something to it and learn something new. You already know how to do the math. You just have to sit down there and generate some numbers and look for patterns. All right, looking for another problem. Oh, this one might be good. Have I used? Yeah, I've already used the backside of that, so new sheet. And we're close to hitting the 2-hour mark. I don't know, do I want to keep going for 3 hours? Stopping at like 2 hours and 15 minutes last time felt good. Well, I mean, if I get in the habit of doing that, then it might take us longer to finish the course, so maybe I shouldn't. Anyway, this problem says in the figure, let me find the figure. Ah, I see. Okay. So in the figure from a previous problem, we've got masses of 10 kilograms and 4 kilograms. Let me actually draw the situation before I finish reading the problem. So we saw this last time, but now it's asking different questions. We've got a rough table. I think last time the table might have been frictionless, but I don't quite remember. I need to draw that pulley bigger because otherwise it forces me to draw the second block in a way where it looks like it's touching the wall over here on the side of the table, and that is not what's happening. Yeah, I need to draw bigger pulleys, or draw my pulleys further to the right. But anyway, we have a 10 kilogram and a 4 kilogram. 10 and 4. 10 kilograms here and 4 kilograms here. And it says the coefficient of static friction between M1 and the horizontal surface, so the coefficient of static friction over here, is equal to 0.5, and that's maximum static friction, of course, but we'll just call it mu static for short, is 0.5. And coefficient of kinetic friction is 0.3. Mu kinetic for the same surface is 0.3. And remember, friction coefficients do not have units. Okay, so questions are, part A, if the system is released from rest, what will its acceleration be? And then part B, if the system is set in motion with M2 moving downward, with the 4 kilogram block moving downward, what will be the acceleration of the system? So those are the two questions. Let's go ahead and draw some force diagrams. So for the 10 kilogram object, or M1 as it's called in their diagram, we've got normal force upward and M1G downward, and we've got force of tension to the right. And if this system moves at all, the direction of motion would be to the right. There's no scenario where this system moves in the opposite direction, so I'm going to go ahead and say clockwise is the positive direction for the pulley. So that tells me that the friction, whether it's static or kinetic, we will confirm in a minute, but the force of friction, regardless of which type, has to be pointing to the left. There's no scenario where it would be pointing to the right. Just doesn't make sense for this problem the way it's been set up. Okay, and for the second object, M2, we've only got two forces, M2G and force of tension. All right, so part A, if system is released from rest. Part A, find, did it ask for both acceleration and tension? No, just acceleration. A system, if released from rest, and part B, a system, if released with M2 moving down. I guess released wouldn't make sense here. If, I don't know, started with M2 already moving down, I'm not sure what the correct word is to replace released here. And I guess a bonus question I could ask is, what happens if somebody kicks the 10 kilogram object to the left and the system is already moving counterclockwise as a result of that when you start observing? What happens then? I guess in that scenario, if you force the matter, then that would be the only time that the system moves with the pulley going counterclockwise. But that wouldn't last for very long, because you've got the natural pull of the 4 kilogram object dragging it back, and you've also got the friction would start opposing that motion. So you've got the double whammy with those two forces working against you. It's only a matter of time. Actually, even in that scenario, even though the motion will be counterclockwise, the acceleration will still be clockwise. Yeah, because there isn't going to be any force to the left in that scenario. If you just give it an initial kick, it's not like you're holding it and continuing to push it to the left. You just briefly gave it some initial velocity and then stopped touching it after that. So that is your bonus question to consider. Anyway, if the system is released from rest. So anytime you are starting from rest and you are given both kinetic and static friction, you have to start with static friction and see if the system will move in spite of that. If it does, then you go back and reevaluate using kinetic friction. Some of you already know that because you did the homework that I told you to do. I had a video that went over, I think it was actually the Pulley homework from 2 weeks ago, I think, or was it last week? I forget when I recommended that you look at it. And for those of you who are new here and don't know what I'm talking about, just click the link in the description that shows the whole course plan and skip down to the force unit, and you will see a bunch of resources, and some of them are just practice problems with video solutions linked right next to them. Anyway, I lost my train of thought. Where were we? Oh, yeah, let's go ahead and assume static friction first, and let's see if the static friction, when maxed out, is able to prevent motion. If it is, problem over. If it's not, then we recalculate and see what the kinetic friction would do. So we've got, I guess I'll write my net force equations. Net force on object 1 in the y direction is going to be 0. Just common sense, this thing isn't going to accelerate up or down. So 10 times an acceleration of 0 gives us a 0 there, and of course we've got normal force upward minus m1g downward gives us normal force equals m1g. We could plug in the numbers, but let's hold off on that and see if any interesting patterns emerge. Net force on object 1 in the x direction is going to be, well, it might be 0 or it might not be. It's going to be the mass of object 1 times the acceleration of the system equals forces to the right, that's force of tension, minus force to the left, that's going to be force of friction. So I'm going to call it just mu. I'm not going to specify static or kinetic here. And then times the normal force equals force of tension minus mu times m1g. Okay, and then net force on object 2 in the y direction, I'm going to use down as my positive direction for the 4 kilogram object, so that's m2 times the acceleration of the system equals m2g minus force of tension. Yeah, down is positive, up is negative for this, so yeah, that should work. And then add the equations to each other, and we get m1 acceleration system plus m2 acceleration system is m1 plus m2 all times the acceleration of the system equals, let's see, force of tension and minus force of tension cancel out, and we're left with m2g minus mu m1g. Okay, if the static friction wins out, then, well, let's figure out what the maximum static friction is. Let's figure out what the force of friction static maximum is. That's going to be equal to 0.5, right? Mu static maximum times the normal force, which is m1g, equals 0.5 times 10 kilograms times 9.8. So that's going to be 5 times 9.8 equals 49 newtons. 49 newtons. Okay, so as long as m2g is less than or equal to 49 newtons, the system will not move. Let's see what m2g is. 4 times 9.8. 4 times 10 is 40, so even if you round up g, it's still less than 49. So that tells me force of friction static less than or equal to 49. In this case, the acceleration of the system has to be 0, so we get 0 equals m2g minus mu static m1g, or rather, I should say minus the force of friction static, not this, minus force friction static, and force friction static, therefore, is equal to 4 times 9.8 is 39.2, which is indeed less than or equal to 49. And that should be newtons, and that should be newtons. All right, and what was the question actually asking? Okay, it's just asking what the acceleration is. The acceleration would be 0 if the system is released from rest. System does not move. Okay, and then part B, what if it is moving? Well, if it already is moving, then static friction need not be considered. Just switch to kinetic friction. So take this same equation. Nothing changed. The direction of the friction is still going to be to the left, and everything else is the same. The only thing that's changed is which friction coefficient to use. So if we go ahead and use 0.3, then we get m1 plus m2, 10 plus 4 kilograms is going to be 14 kilograms times the acceleration of the system equals m2g, which is 39.2 as we calculated earlier, minus 0.3 times m1g, 10 times 9.8. Well, 0.3 times 10 is 3, and 3 times 9.8 is 29.4, and 39.2 minus 29.4 is exactly 9.8, so 14 acceleration of the system. I probably should have kept this as 4 times 9.8. 4 times 9.8 minus 3 times 9.8 is 1 times 9.8, so that's another way you could have gotten this. But yeah, 14 acceleration of the system equals 9.8. If we divide both sides by 14, then we get 0.7. And I know that because I'm a nerd. It helps to know your 14 times tables. 14 times 7 is 98. 0.7 meters per second squared. And that came out positive, so I know that this system is actually going to be accelerating in the clockwise direction. It doesn't have to. If the coefficient of kinetic friction were just a little bit higher, let's see, how much higher? Well, 0.4 would just give you 0 acceleration for the system, and in that case the system would just continue moving clockwise until, of course, the 10 kilogram block collides with the pulley. That's when things would change, but otherwise it would just move with a constant speed if the coefficient of kinetic friction was 0.4 instead of 0.3. And we already saw that 0.5 would prevent the system from moving. Well, if the system is already moving, then the coefficient of kinetic friction can be as high as you want. But yeah, any higher than 0.4, any coefficient of friction higher than 0.4, if the system is already moving, it won't immediately stop moving, but it will slow down and then come to a stop, and then if it's at least 0.4, it will stay stopped from that point on. Actually, I guess in any scenario where the coefficient of kinetic friction is high enough to cause the object to decelerate. Once it comes to rest, it will stay at rest from that point on, because that would necessarily mean that the coefficient of static friction is high enough to prevent it from starting up its motion again. That probably sounded like a bunch of mumbo jumbo to some of you, but try and think about it. I could reword things to make them more clear, but I think I'd rather just leave you guys with the conclusion there and try to work out the meaning of what I said. That might be a helpful mental exercise. What to do next? I guess I can write this over here. A system equals 0.7 meters per second squared. Oh, and by the way, for these past couple problems, I've just been assuming that these objects will have accelerations of the same magnitude. I know I talked about it before when talking about systems, but it bears repeating. Why do we assume that? Because it's just kind of common sense. If you release a system like this from rest, then there's no scenario where the 3 kilogram object is going to accelerate faster than the 5 kilogram object. The 5 kilogram object is what's dragging it, so it can't really go faster than the 5 kilogram object pulls it. And I guess you could think about it in the opposite direction. If the 5 kilogram object was moving slower than the 3, then that just means that the rope would loosen, because the 5 kilogram object would be trying to lag behind while the 3 kilogram object is catching up. The rope would just eventually, instead of being completely straightened out, would eventually just kind of bend and go slack. And then the tension would change, or just outright disappear. So we don't imagine that happening. Just from everyday real life experience, we see that doesn't happen, so that's why it's fair to assume that these objects have the same magnitude acceleration at least. Similar reasoning applies over here. If the 10 kilogram object was moving faster than the 4 at any time, then the rope would just start to loosen. If the 10 kilogram object was moving slower than the 4 kilogram object, that would be straining the rope too much, and eventually the rope would have to snap in order for the 10 kilogram object to fall behind. So either way you think about it, whether this object is moving faster or slower than this one, you're going to encounter something that just doesn't really happen in everyday life. Maybe if you really forced it, if somebody grabbed this 4 kilogram object and really shoved it as hard as they could in a downward direction, that could cause the rope to snap, because you're forcing the 4 kilograms to move down faster than the 10 kilograms can be dragged. Yeah, at that point, the rope could snap. If you use something flimsy like just a piece of thread, you could see that happening. But then the problem would actually mention something about that to let you know it's a possibility. They would tell you something like, oh, this rope or cable or string can support a maximum tension force of whatever number they give you. And yeah, at that point they could ask you like a bonus question of, how fast will this object move, or for how long will it continue to move before it gets slowed down by friction if the rope snaps? And how long will it take before the rope snaps, I guess, could be a question they could ask. Well, I guess that would require tension changing over time, which I can't see that being a Physics 1 problem, but I could see them setting up something like that for Physics C, something calculus-based. I'm going to need to think on that. Maybe I can come up with a problem for that, or at least find one in one of my books. Although, if there was one in one of my books, I would imagine that I'd be able to remember it, because I've gone through my books a number of times. I know I haven't read every single problem in them, but I would think I would have noticed if a problem like that was in there. But now I'm rambling. Let's move on and find something else to work on. And I think I've already found it. Here's a good problem for people who still believe in the myth of normal force being equal to mg. So it says, a 1,000 Newton crate is being pushed across a level floor at a constant speed by a force of 300 newtons at an angle of 20 degrees below the horizontal, as shown in the figure. I'll go ahead and draw it. That is not very horizontal looking. Let me try and fix that. Oh my goodness. What did I do? Maybe I should have brought out a ruler for this. Okay, that will just have to do. And they said it was a 1,000 Newton crate. They said this crate was 1,000 newtons. So force of gravity on it is 1,000, and then divide that by 9.8 to figure out its mass. It's going to have a normal force on it, and it has a force applied at a 20-degree angle of 300 newtons. So there is force applied equals 300 newtons, and it is at an angle of 20 degrees. I don't even know if that's very readable at that size, but 20-degree angle with the horizontal. Okay. Let's read what the rest of this says. So, part A, what is the coefficient of kinetic friction between the crate and the floor? Oh, let me see. It's being pushed across a level floor at a constant speed by a force of 300 newtons at an angle of 20 degrees below horizontal. So yeah, part A, what's the coefficient of kinetic friction between the crate and the floor? And then part B, if the 300 Newton force is instead pulling the block at an angle of 20 degrees above the horizontal, what will be the acceleration of the crate? Assume that the coefficient of friction is the same as that found in part A. So part A is asking, and I haven't finished drawing the diagram, by the way, but part A is asking, what is the coefficient of kinetic friction? And part B, acceleration if force applied is directed at an upward angle instead, at an upward angle instead. And I guess I'll have to draw a second diagram for that when the time comes. Okay. We have one more thing to draw on our diagram over here, which is the force of kinetic friction. They already said the object is moving, so we know it's kinetic friction. And to top that off, they said it was moving at a constant speed, and based on the drawing, you can reasonably assume that it's also in a constant direction to the right. So it's a constant velocity. And what does that mean? So force, friction, kinetic is over there and acting to the left. And I guess just for clarity's sake, we'll also say it has some sort of velocity to the right. If you see velocity on your force diagrams, I think this might actually be the first... No, this isn't the first time we've seen it. But if you see velocity on your force diagrams, it is not a force. Remember, velocity is not a force. It's just where the object is currently moving. It has no bearing on any forces except, of course, the kinetic friction force, because the kinetic friction force, or static friction force for that matter, but... Oh, yeah, I guess you could have a velocity when there's a static friction force. We did problems like that one truck problem from, I think it was 2 weeks ago. Anyway, the direction of velocity, particularly for the kinetic friction force, is going to help you determine the direction of your friction force. But otherwise, it is completely separate from the rest of your force diagram. Don't let it fool you into trying to draw forces in its direction when there's no reason for them to actually be acting in that direction. Velocity does not imply anything about force except help you figure out which direction your friction forces might point. That is it. The fact that this velocity is constant tells us that the acceleration must be zero. This is an object in static equilibrium. So acceleration must be zero, which tells us then that net force must be zero. Okay. Let's go ahead and break up our force applied into two components. So it's going to have a component to the right, which is going to be the cosine component, and a component downward, which by process of elimination would have to be the sine component. So for our equations, that just means, let's see, for vertical, I guess I'll do it over here, net force in the y direction is going to be forces up minus forces down is going to be 0, equals normal force minus downward, we've got force applied sine theta, so 300 sine of 20 degrees, and also minus 1,000 newtons. I don't know why I wrote the newtons in there. I usually save that for last. And then I guess that allows us to solve for normal force, and net force x also has to be 0, equals forces to the right, so that's going to be force applied times cosine of 20, so 300 cosine of 20 minus force of friction kinetic, which is going to be the coefficient of kinetic friction times the normal force. Okay, we can solve for the normal force up here, so add 1,000 and add 300 sine 20, so adding that to 0, of course, so 1,000 plus 300 sine of 20 is 1102.606. I'll round it to 1102.61. Or you know what? I'll keep 3 decimals. Normal force equals 1102.606 newtons. And then if I go ahead and add mu k normal force to the 0, then that's going to make it equal to 300 cosine 20. So mu k times 1102.606 equals 300 cosine 20 divided by 1102.606. So 300 cosine of 20 divided by 1102.606 is 0.25567. I'll round that to 0.256. So I'm getting mu k is equal to 0.256, no units. Coefficients of friction are unitless. All right, and part B, what's the acceleration if the force applied is directed at an upward angle instead? So if I were to redraw the diagram, but this time the force applied is upward at 20 degrees. I guess I could draw the 20 degrees there, or I could draw it over here. It doesn't really matter. Either way, that angle, 20 degrees. And then force applied, that's probably not even very readable. And then everything else in our diagram remains the same. Normal force there, force of gravity there, force of kinetic friction here. Okay, in this scenario, cosine component is still our horizontal component. Sine component is vertical, but this time it's vertical and up. So the only thing that really changes is in our equation over here, this becomes plus 300 sine of 20, and the rest is history. So yeah, just rewrite. Just take this and rewrite it. New net force Y is equal to, well, actually both equations change because net force X is not 0 anymore. So net force Y is going to be 0 still, equals normal force plus 300 sine 20 and then minus 1000 versus net force X is going to be equal to the mass, which we don't know yet. We know it's mg equals 1,000, so divide by g, m equals 1,000 over g. So 1,000 over g, that's your mass, times the acceleration in x, we don't know yet, equals forces to the right minus forces to the left. So that's going to be 300 cosine 20 minus, this time we're going to have a smaller friction force because we're going to have a smaller normal force. But the coefficient of friction is the 0.256 we calculated earlier, so 0.256 and then times normal force we don't have yet. But we'll find out pretty soon. In fact, that's the next thing we're going to calculate. So pick a color. How about you? So let's see. If I do the net force y equation over here, then add 1,000 to the 0, subtract 300 sine 20. So 1,000 minus 300 sine of 20 is equal to normal force. That's 897.394. 897.394. Normal force for part B is 897.394 newtons. And plug it into here, and we get, let's see, 1,000 over, I guess I'll plug in g is 9.8 times the acceleration in x equals 300 cosine 20. So 300 cosine 20 minus 0.256 times 897.394. I'm getting 52.1749. I'll round that to 52.175 equals 52.175. Okay, multiply by 9.8 and divide by 1,000. 52.175 times 9.8 and over 1,000 gives me 0.5113. I'll just round that to 0.51. So my acceleration in the x direction is 0.51 meters per second squared. And there we go. This problem illustrates why you've probably done this without knowing why you did it. This problem illustrates why, when moving furniture, sometimes it is helpful to push your furniture at an upward angle, because what that does is it reduces the normal force that is needed to support the object. And by reducing the normal force, of course, you reduce the amount of friction that you have to overcome to get the object moving. So yeah, if you're struggling to push something like a table or a sofa, try pushing at an upward angle. That might just be what you need to make things move. How are we doing on time? We're 2.5 hours in. Let's see if we can find some more problems to look at that might be worthwhile. And of course, there's going to be plenty more. I think we have enough material for at least 2 more sessions of this. Especially because I haven't even begun to look at the problems in the OpenStax book, although I'm not entirely sure how good those problems are going to be after what happened the last time I tried to pull problems from that book. They're better than nothing. You know, it's better than having no textbook at all. But yeah, if you want a textbook with good problems, then my recommendations are, I know I showed these before, but College Physics by Sir Wayne Fawn. This is the 7th edition. There's probably a much newer edition out right now, but it doesn't matter. Just buy an older edition on the cheap. Buy a used copy, it'll be fine. Or for Physics C, the book I like to use is this, even though it does go a little bit beyond what well, maybe more than a little bit beyond what you need for Physics C. Physics by Resnick, Halliday, and Crane. Those are the 2 books I use, and those are the ones I'm familiar with, and if you get recommendations from other people, then I can't speak to those because I haven't tried those other books. Let's find a problem now. This one maybe? Let's see. A hockey puck is hit on a frozen lake and starts moving with a speed of 12 meters per second. 5 seconds later, its speed is 6 meters per second. Okay, so it's asking for the acceleration, which we can figure out. Asking for the coefficient of friction, and asking how far it travels. I mean, okay, why not? We can do it. It's fairly simple. I'll skip the third part, which is just asking us to do some more kinematics. I'd like to focus mostly on the force side of these problems, but it's still important to get used to doing kinematics with force. And oh boy, do I have a problem where you're going to need to really draw on your kinematics skills from before. But that problem is probably going to be coming up next time, not today. But I definitely want to cover it no matter what. Anyway, hockey puck is hit on a frozen lake and starts moving with a speed of 12 meters per second. So here's a hockey puck. I'm just drawing it from the side view. And, oh, that doesn't look very horizontal, but we'll pretend it is. Hopefully that straightens it out a little bit. But yeah, V initial, they said, is 12 meters per second. They said it slows down to 6 meters per second over the course of 5 seconds. And the first question, of course, is asking for its average acceleration, which we can calculate. V final minus V initial over t. Or you can use the first kinematics equation if you want. If you assume the average acceleration acts as a substitute for some constant acceleration, that works just fine. You get 6 rather, equals 12 plus acceleration times 5. Subtract 12, you get -6. -6 over 5 is -1.2 meters per second squared for your acceleration. So that's part A. And then part B is the most important part for me. What is the average value of the coefficient of kinetic friction between the puck and the ice? They never told us the mass of the puck. Are we stuck? Well, let's do the math and see. So this thing is going to have force of gravity mg acting downward and normal force acting upward, and there's nothing pushing it to the right. I'm assuming right is its initial direction. So I guess I'll write V initial is to the right like that, which would then mean that the kinetic friction acting on it must be to the left. Force of friction kinetic must be acting on it to the left. All right, so if I go ahead and write my net force equations, net force, I'll do y direction first, has to be 0 equals, I'll do forces up minus forces down, normal force minus mg. Okay, so in this case, normal force is just equal to mg. This implies that mg equals our normal force. Okay, net force horizontal is equal to the mass times the acceleration horizontal. I guess I should call that acceleration in x. Equals forces to the right, nothing, minus forces to the left, that's the force of kinetic friction, equals negative coefficient of kinetic friction times normal force, equals negative coefficient of kinetic friction times our normal force is equal to mg. So mass times acceleration in x is equal to negative coefficient of kinetic friction times mass times g. Divide both sides by mass, and would you look at that, the mass did not even matter. Okay, and our acceleration was negative 1.2 equals negative mu k times g. The negatives cancel out, and divide by g. 1.2 divided by g is 0.122. So we get a coefficient of kinetic friction of 0.122. Pretty reasonable. I'd expect it to be quite low because this is ice we're talking about. There's hardly any friction there. I think we have time to do just one more. Oh, let's do this now so that I don't forget to do it later. I talked about this last time, I remember. Here's a problem where air resistance needs to be taken into consideration. It's a very simplified air resistance problem, and this is basically the most that they could ever ask you for Physics 1. Physics C students will learn more about the calculus of air resistance later once we finish simple harmonic motion and go back to redo the course with calculus. So 43 in my book, it's an object falling under the pull of gravity is acted upon by a frictional force of air resistance. The magnitude of this force is approximately proportional to the speed of the object, which can be written as F equals BV, force of air resistance. I'm going to call it force D for drag. Air resistance is sometimes called drag. Air resistance aka also known as drag, I will represent with FD. Sometimes I might also represent it with FR, force resistance. Or usually I will save FR for some other type of resistive force which is not necessarily air resistance, but we'll see those whenever we see problems involving them. So yeah, force drag, they said, obeys the formula BV in this case. Sometimes it's BV, sometimes it's BV squared, and sometimes it's some combination of both, like B1V plus B2V squared. But typically it's going to be either a BV or a BV squared relationship. So I guess to give you some intuition as to what these mean. The faster you move in the air, the more air particles that you collide with. And as you collide with more and more of these tiny air particles, they bounce off of you, and even though they're tiny, all those little microscopic bounces add up and slow you down. They nudge you backward a little bit as you move. Whatever direction you're moving, you bump into them, you bounce them forward, they bounce you backward. You bounce them forward faster than they bounce you backward. But still, the faster you go, the faster you run into these particles, the more of them you run into, the more of those collisions you have. That's why it's related to your speed, but also it's related to how many of those air particles you catch. So this B factor is basically, it depends on things like the density and surface area. I know I talked about this a little bit when we discussed projectile motion. But yeah, that's what this B factor is about. Shape, size, surface area, stuff like that. I guess surface smoothness might also have something to do with it. All of that is accounted for by this B factor. So that's just the intuition behind the equation, just understanding what it's about. So it's giving us, assume that B is equal to 15 kilograms per second. It says assume B equals 15 kilograms per second. That's just the units that it has to be, because the speed, which is going to be in meters per second, if you do meters per second times something, needs to equal newtons. I guess we'll work this out. So force, newtons, has to equal whatever the units of B are times meters per second. Newtons, if you don't remember, is kilogram meters per second squared, and you have several ways of getting this. We could just use, for example, force of gravity equals mg, or we could even use net force equals ma to figure this out. That would give us newtons equals kilograms times meters per second squared. So a newton is a kilogram meter per second squared. Kilogram meters per second squared equals whatever the units of B are times meters per second. If we cancel meters on both sides and we cancel seconds on both sides, we're left with B has to be in units of kilograms per second. I wonder if there's actually a formal notation for this, because this is just, if you do this on your test, they're going to look at you like you're crazy. But I don't know if there's actually some sort of proper notation for showing that the units of a thing times or divided by the units of some other thing equals the units of a third thing. I don't know if there's any sort of formal notation for that. Maybe I should try and Google that. I never thought to look that up. But yeah, so B is in units of kilograms per second because it has to be. And I guess intuitively you could say it's like the total, I don't even know, kilograms of body mass colliding with air particles per second? I'm not sure. I'm going to have to think about that to figure out why intuitively kilograms per second would make sense. But anyway, where did the problem go? Yeah, there it is. Assume that B equals 15 kilograms per second, and also assume that the mass is 50 kilograms is what they gave us. More of this problem has been rambling than actually doing the problem. Part A, it's asking, what is the terminal speed the object reaches while falling And then part B, does your answer to part A depend on the initial speed of the object? Explain. So let's start with part A. Part A is asking, what is the terminal speed? Terminal speed or terminal velocity. V terminal. V terminal. We'll call it VT for now, but we're going to use the T for something else in a future chapter, so maybe I'll just write out the word term in the future. But for now, we'll just call it VT, terminal velocity. You've probably heard of this concept before, terminal speed or terminal velocity. Basically, if an object is moving and subject to air resistance, there's going to be some sort of velocity that it reaches, and once it reaches that velocity, it stays at that velocity until, of course, the forces acting on it change. Since air resistance grows with your speed, the faster you go, the more air resistance tries to slow you down, and eventually you reach a speed where the slowdown is completely canceling out whatever is moving you forward, and at that point you don't speed up or you slow down, you just stay at that velocity. If somebody is falling from like an airplane, at first they're speeding up, but eventually the air resistance acting up on them matches the gravitational force acting down on them, and at that point, whatever speed they're at, that's the fastest they will go until they hit the ground or open a parachute or something. So yeah, here we have a falling object. Let's go ahead and draw its diagram. So I'm just going to draw a generic block. It's going to have a mass, which was 50 kilograms. It's going to have, of course, force of gravity acting downward on it, and it's going to have the drag force or air resistance force acting up on it. So terminal velocity is when the object is basically in equilibrium. Terminal velocity is when the acceleration hits 0. So when the object first drops, its velocity is 0, and it just has a net acceleration downward. But then 1 second later, there's some velocity and a tiny amount of drag force versus the same force of gravity down. So it would still be accelerating down, but not as fast. And if you were to graph it, if you were to graph its velocity over time, then, if you dropped it from rest, at first, it would be speeding up quite a bit, but the faster it goes, the more air resistance it encounters, and its downward acceleration starts to slow down and down and down. We'll say that down is the positive direction for this problem, so that my graph is still accurate. And eventually it just kind of levels off, and that's where your terminal velocity is going to be. That's where your, whatever this is your V terminal. Anyway, so we're just asking what happens at the end after a very long amount of time has passed. We would say net force vertical at that point has to be 0, which tells me, we said down was positive, so I'll say force of gravity minus force of drag. Not that it matters which direction is positive for this equation. We get the same result either way. Drag force equals gravitational force. BV, or not just any BV, BV terminal specifically equals mg. And then, let's see, divide by b because we're solving for V terminal. So that's mg over b. And just plug in the numbers that we know. So that's going to be 50 kilograms times 9.8 meters per second squared, divided by 15 kilograms per second. 50 times 9.8 over 15, and that should be in units of meters per second. Let's see what I get. 50 times 9.8 over 15 is 32.667. Just a bunch of repeating sixes. I guess 32 and 2/3 if you prefer to be more exact. 32.67 meters per second. There we go. So that was part A. Part B. Does your answer to part A depend on the initial speed of the object? Explain. Actually, I think I want to leave this as homework for you guys to think about. What happens if, so at 32.67 meters per second, the drag force upward evens out with the gravitational force downward. And I already said, if you start from rest, or if you start really anywhere lower than 32.67 meters per second, then you will speed up until the drag force builds up to whatever amount it reaches when your speed is at 32.67. So if you start from lower than 32.67, you build up to 32.67 and don't continue to go up past that point. But what if instead of releasing the object from rest, I forcefully threw it downward, forced it to have a downward velocity greater than 32.67? What happens in that scenario? Just intuitively, what would that look like on a graph like this? If you were to add more to this graph, I guess I would have to make this vertical axis longer and start you somewhere higher on the velocity axis. What would that graph look like? Just keep that same dotted line for your terminal velocity and just make an intuitive guess as to what that graph would look like. And to help you with constructing that graph, try and figure out what's happening with the acceleration second per second per second, 1 second at a time. You know, start with a velocity of, I don't know, make it 100. And then ask yourself, 1 second later, approximately, what would the velocity be? 2 seconds later, what would it be? And each second you also have to recalculate, you know, what the drag force changes to and what the net force and acceleration become. And see if you can piece together what that would look like. So that I will leave as homework in addition to whatever bonus questions I asked for you guys to try out. I'm not necessarily going to answer all of those bonus questions that I asked throughout this stream, but at the very least I will go over this one. And I think that is it. Any other announcements? Traditional office hours. I, yet again, had another busy week and haven't really had time to think about what I want to cover yet, but I will probably have an opportunity to do something, if not tomorrow, then maybe Tuesday, a little bit later in the day than I usually stream. But I might be able to do something on Tuesday. We'll see. Not making any promises, but might be able to do something tomorrow or Tuesday. Something more calculus focused. I mean, I have some ideas of what I want to cover, but there's this one problem that I would really like to just do on my own first before I stream, because I feel like doing it live, I'm just gonna mess it up too badly. I don't even know what the outcome is gonna be, is the problem. So I would like to just kind of calculate ahead of time and make sure I have an organized way of presenting the problem. It's a very common question in physics that I don't really see any good online answers for, like in the physics forums and whatnot. At least none that I've been able to find, but maybe I'm just not looking hard enough. So that is something I would like to do. So yeah, if I can get that ready, then maybe we will see one within the next 2 days. Otherwise, maybe next week. Okay. Any other things? If you haven't done any, let me go ahead and open it. If you haven't done any of the practice questions that I recommended over here, you might want to, because the problems I'm going to present are, some of them are going to start getting even harder. If you thought today was hard, I mean, several of the problems we did today were rather simple, but had some teachable moments in them. But we will see harder problems. They're coming. They're coming. But if you're having trouble following with what we did today, especially some of the tougher problems, then you might want to pick out some of these problems and try them out. And remember, this book does have an answer key for some of the questions. I think it's not always strictly odds or strictly evens. It seems to alternate section by section. But yeah, you do have an answer key for some of these, so maybe look ahead at the answer key first and see which ones are answered and prioritize those. And if you're getting matching answers, then do similar problems on your own once you feel like you understand how to do them. And of course, if you get stuck on any of these, I mean, you could leave a comment and request that I do it in the next stream, or just show up during the stream and ask about it. That can work too. But otherwise, I'm just going to continue with my plans. I've got 2, maybe 3 more sessions of this, and then we can finally move on to another topic. I know some of you probably want to move on right away, but I think it's really, really important to do a lot of force problems, so that's what we will continue to do. Anyway, that'll be it for today. Where did my mouse go? There it is. Yeah, that'll be it for today. Take care, study hard. I know some of you have final exams, so good luck with that, and have a good winter break. I will still be streaming through winter break because I'm not a holiday guy, so if you're bored during the holidays and you've got nothing better to do, you might as well come here and learn some physics. Anyway, that is it for today. Take care, and I'll see you in the next one.